So we will start discussing non-volatile memories, or NVMs. Non-volatile memories are memories whose content remains the same if you disconnect the power supply. The main importance of non-volatile memories, in the past they used to be used to carry setup information, for example, in the BIOS of a system, and that was it. But currently, the main importance of NVMs is that they form the mass storage devices of choice in most mobile media. In the past, most mass storage on PCs took place in hard disks, which stored stuff on magnetically programmed drums, and they read it using movable heads. The fact that this storage mechanism was so dependent on mechanical and moving parts was not suitable for mobile platforms. We need something that is solid state, that doesn't have moving parts, that is more reliable, and that is faster and has less power consumption. And this is where NVMs come in. They form the only way of solid state mass storage that we have available. So NVMs are built on the same array structures as ROMs. So we will find ourselves dealing with NOR NVMs and with NAND NVMs. And they are more or less ROMs for all intents and purposes. So when we see how we read from them, you will find that we read from them the same way we read from ROMs. If you think about delay during read operation, it's the same way we calculate delay in a read operation for a ROM. So the only difference here is that the way we decide if there's a stored 1 or a stored 0 in a ROM, whether it's a NOR ROM or a NAND ROM, is whether the cell has a transistor or not. So the only question we have is, does it have a transistor or not? Which is why ROMs are read-only, because once you have fabricated them, you cannot undo the fact that there is a transistor in the cell, or you cannot undo the fact that there is no transistor in the cell. So it's actually set in stone. Literally, you have set it in stone. So the whole idea about NVMs is, how can we make the fact that there is a transistor or there isn't a transistor in the cell reprogrammable? How can we make it not set in stone? And so the whole idea is, how can you have a transistor in the cell, and that this transistor can be made to disappear or appear based on what we want to write in that cell. If we can do this, then this memory does not become, strictly speaking, read-only. It becomes sort of writable, and that is exactly what we want to see happening. So the idea, we kind of saw something like this when we looked at the layouts of NAND ROMs and NOR ROMs, because we used implants, threshold raising implants and threshold lowering implants in order to reduce the programming of ROMs to a single mask. If we can have this operation, the threshold raising and threshold lowering become an operation that can be done on the fly while operating the memory, then we can make the memory basically writable. And so the whole idea is, if you can have a transistor whose characteristics can be moved between graphs A and B, then you have done what we have required here. So this is a transistor whose threshold voltage can be changed between two values, V threshold 1 and V threshold 2. If V threshold 2 is so high that it is actually higher than the supply voltage we are using, then for all intents and purposes, this transistor does not exist. So we can actually program the transistor to not exist, because its threshold voltage is so high that we will not be able to turn it on while operating. If the transistor characteristics can move back and forth between the two characteristics, then we have a non-volatile memory, because we can change the value written in the cell between 0 when the transistor doesn't exist and 1 when the transistor exists, if we are looking at a NOR ROM. So just to set the terminology, when we push the transistor to characteristic B so that it doesn't exist, we don't actually call this writing, we call this process erasure. And when we push it back to characteristic A so that it exists, we call it programming. Whether you call programming or erasure, whether you call one programming or the other erasure is a matter of convention, but you should not call these processes writing, because the word writing is usually preserved for actual writing in SRAM or DRAM cells, which is very different from programming and erasure here. Because programming and erasure are not just about writing a specific value at a specific node in a circuit. They are about changing the whole characteristics of a device. And so the idea for almost all non-volatile memories, and we are going to discuss a lot of non-volatile memories in detail, but the main idea behind all non-volatile memories is that we have double gate MOSFETs. So we don't have a MOSFET with a single gate, which we call the control gate. So this G is actually a control G. This is the gate that we see in a normal MOSFET. We also have another gate which we call the floating gate, which is in the middle of the oxide. This floating gate is obviously not accessible because it doesn't have a terminal through which we can access it. It is just floating from within the oxide. But if you imagine that somehow you manage to put a lot of charges, a lot of negative charges, electrons on this gate, then these electrons are going to raise the threshold voltage of the transistor. Why are they going to raise the threshold voltage of the transistor? Because more or less they form an implanted channel, and this implanted channel requires the control gate to put a higher VGS in order to turn on the transistor. In other words, when you put a positive voltage here, these negative charges are going to create a counter field going up, and therefore you will need a much higher field coming from the control gate in order to invert the true channel. Now, if these electrons in the floating gate are pushed back out of it, then we can actually return the transistor to its original V threshold. So the process of bringing electrons into the floating gate and trapping them into the floating gate is the process of erasure or programming, and pushing them out is the opposite process, where we return the transistor back again to its A characteristics, the characteristics with the smaller threshold voltage. And so if you look at this table, you will find that I'm listing the 4 kinds of non-volatile memories I will discuss: EPROMs, double EPROMs, NOR flash, and NAND flash. These are the 4 most important non-volatile memories, and specifically these 2 are really important. So I'm comparing them here in terms of the device used for storage, and I'll discuss these devices in detail in terms of the programming method and the erasure method, which is how do we bring the electrons into the floating gate, and how do we push the electrons out of the floating gate. And I compare them also in terms of programming speed, erasure speed, write cycles, and density. And it's important to discuss what each of these mean. So programming speed means how long it takes to change the transistor from characteristic A to characteristic B. Erasure means how long it takes to change it from characteristic B to characteristic A. So some of the mechanisms used to program or erase the memory can take longer than others. Write cycles means how many times a specific cell can be programmed and erased. So some of the programming and erasure mechanisms actually take a toll on the cell. And so if you keep doing them, the cell degenerates with time and you cannot program it or erase it again. It becomes stuck at a specific value. So some of the mechanisms take more of a toll than others, and so we have to compare them in that respect. Density, of course, is easy to see because it's just how many bits you can pack in a certain area. Now, there are 3 programming and erasure mechanisms that you can see in the table, and we will discuss each of these now. And when we discuss the specific memories, we will pick one of the 3 mechanisms for both of erasure and programming. To be absolutely clear, for a specific memory, you don't have to use the same mechanism for both erasure and programming. One could use one mechanism and the other could use another. So the 3 mechanisms are Avalanche breakdown. This is the first. The second is Fowler-Nordheim tunneling. And this is a kind of tunneling, but it is not similar to the direct tunneling we discussed in Module 10. It's related, but it's a little bit different. And the third is the hot carrier effect, which we discussed in detail in Module 10, and specifically here we call it hot carrier injection, because it's not just a side effect or a secondary effect that we observe, it is something that we are doing intentionally and trying to benefit from. So avalanche breakdown is really simple. The whole idea is you have a floating gate, a control gate, and there's silicon dioxide between the floating gate and the substrate. And the question is, how can you get electrons to go from the substrate to the floating gate? If you can get them to the floating gate, they will be trapped there and your job will be done, because the floating gate is surrounded by oxide from all sides, and electrons do not normally flow through the oxide. So we want them to flow through the oxide while we are programming, and we want them to flow back through the oxide while we are erasing, but they don't usually do that. So we have to do something really special. And so the first really special thing we can do is avalanche breakdown. And this happens when you apply a really, really high positive voltage to the control gate. And this, you'll find that this is generally true while we are programming and sometimes when we are erasing, that we apply an abnormally high voltage to the control gate. And by high voltage, I don't mean supply voltage. I mean a voltage that is much higher than the normal supply you would be using during operation. And so this very high voltage imposes a very high electric field throughout the oxide, right? So what's going to happen here is that this very high electric electric field is going to attract some electrons from the substrate into the oxide. These electrons are usually stopped within the oxide, they can't get through it, but what's going to happen is that these electrons are going to hit some of the atoms of the silicon dioxide, and when they hit these atoms, they release electrons. They release more electrons than the electron that hit them. And these electrons themselves are very energetic in the field. They hit more atoms and release more electrons. And so you get a chain reaction similar to a nuclear reactor, and you get more and more electrons, and the oxide basically becomes a conductor temporarily, and these electrons all flow upwards against the direction of the electric field. As soon as they meet the floating gate, they settle there. Now, this process is self-limiting, and most programming operations are self-limiting, because the more electrons gather within the floating gate, the weaker the electric field below the floating gate will be. So more electrons gathering, weaker field, weaker programming effect. So it's self-limiting, but you only need as many electrons to gather at the control gate so that you can raise the threshold voltage of the transistor to the level that you want. Now, can avalanche breakdown actually be used to erase the gate? It cannot, because you can't really apply a high positive voltage in the reverse direction, and so avalanche breakdown only happens in a certain direction, and therefore it can only be used for programming. You can see that avalanche breakdown is actually a pretty slow process. So if you look at the programming speed of memories that use avalanche breakdown for programming, you will find that it is slow. Avalanche breakdown is also a very harsh process. You are basically breaking down the insulator. And therefore, you'll find that the programming cycles of memories that use avalanche breakdown are low. You can reprogram them only only a limited number of times before they don't work anymore, because the insulator is basically going to be too porous and it's going to be almost conducting all the time. So this is obviously a very brutish way of doing things. Something that is a little bit more gentle is the hot carrier effect. And we discussed the hot carrier effect in detail in a video in Module 10. But the hot carrier effect is basically a classical effect. It can be understood fully using the band model. There's no quantum effect happening here. Some electrons are going to be very energetic in the conduction band of the substrate. They're so energetic that they gain enough energy to overcome the barrier imposed to them on the oxide. This barrier is a little bit over 3.5 electron volt, and if they get enough energy to overcome it, they can then flow through the oxide. If they flow through the oxide and go to the polysilicon floating gate, they will settle there. Now, why would we have high energy electrons? We have high energy electrons near the drain usually because they are flowing very fast. And so this happens in velocity saturated and especially in transistors with velocity overshoot. So the electrons have so much kinetic energy, we call them hot electrons. They are not at the edge of the conduction band. They are high in the conduction band, high enough to overcome the barrier of the silicon dioxide, and so they can move through the oxide. But in order for them to flow through the oxide, there has to be an electric field. And this electric field, this vertical field, is applied again through the control gate. And so this imposes a vertical field that promotes the motion of electrons into the floating gate. Again, this is a self-limiting process because at some point the charges in the floating gate are going to cancel any field through the oxide to the substrate, and therefore even if you do have really energetic charges at the drain, most of them are not going to go to the floating gate because there's no vertical field promoting their motion into the gate. Now, hot carrier injection is a lot faster than avalanche breakdown. In fact, it's really fast. It's the fastest method we can use for programming. The problem with it is, number one, we cannot use it to deprogram. We cannot use it for erasure because erasure means we are pushing electrons down from the floating gate back into the substrate. And because the electrons in the floating gate are immobile, they are fixed, and there's no way to get them moving, then there's no way to get them hot. We need electrons to be hot so that they can actually observe the hot carrier effect. And there's no way to do that while they are trapped in the floating gate. Hot carrier effect has a medium impact on the oxide, meaning that it is a lot gentler than avalanche breakdown. There's nothing as bad as avalanche breakdown, but it's not ideal, right? So it's programming cycles are kind of intermediate between avalanche breakdown and the last method we use for programming and erasure, which is Fowler-Nordheim tunneling. So this is tunneling. So it's a quantum effect. It's the same kind of tunneling we talked about in module 10. So it does not actually require the physical motion of electrons within the oxide. It is more related to uncertainty and the wave-particle duality of electrons. And when we discussed tunneling, we found that the main determining factor of probability of tunneling is the thickness of the oxide through which we are trying to tunnel, the thickness of the insulator through which we are trying to tunnel. The smaller the thickness, the more likely the tunneling. Now, in an NVM, we don't want tunneling to happen all the time. So we shouldn't actually make the oxide here too thin, right? We should keep it reasonable so that we don't have tunneling when we are normally operating the array. Because notice that most of the time we are reading from the array. We don't want to change the values within it. We are reading from it. At its heart, this is a ROM still, right? We can change its contents, but it is a ROM. So we don't want the oxide, the thickness of the oxide, to be too small. But we want to sometimes be able to tunnel through it. So what we do here is we apply a very large vertical field. Very large vertical field is applied by putting a very large control voltage on the control gate, VPP. And so you notice that when you are programming, and in fact when you are erasing, you generally apply this huge programming voltage because you need large electric fields in order to program. Whether you're doing the hot carrier injection method, avalanche breakdown, or Fowler-Nordheim tunneling, you need a large vertical field. And so with the very large vertical field, what happens is that the oxide is going to tilt, and the tilt is going to be very sharp because there's a huge drop on this oxide. This is the oxide that lies between the floating gate and the substrate. Now, with the oxide tilting so much, there is a portion of the oxide which is now basically triangular instead of rectangular. So the oxide is more or less rectangular for most of its range, except when it's bent so much. When it's bent so much, a large portion of it is going to be triangular. And the thickness that you observe in this triangular part is much smaller than the thickness you observe if you had to tunnel through the whole oxide. And now, so it's easy for electrons on this side to tunnel to the other side, with the application of this large electric field. When you remove the programming voltage VPP, this large bending or tilting in the oxide is going to resolve, and the thickness observed by electrons is going to be large once again, and they cannot tunnel, which is something that we want. Now, what are the advantages of tunneling? It's very gentle. The electrons are not actually passing through the oxide. It's a quantum effect. So it has great programming cycles. It can also be used for programming or erasure, because we're not depending on the electrons being hot. We don't want them to be moving. We don't need them to be moving. They can be still, and they will still be able to tunnel to the other side. So we can actually use this for erasure. We can actually use it to pull electrons back into the substrate from the floating gate. The only disadvantage of Fowler-Nordheim tunneling is that it is pretty slow. It is slow, especially relative to hot carrier injection. So it's not much slower than, it's not actually slower than avalanche breakdown, but it is slower than hot carrier injection.